So this week we are going to flip the script, literally, like 90 degrees. We're going to look at objects that move in one dimension vertically. So up and down. Instead of going left and right along a road, we're going to go up and down toward the sky and down toward the ground. So when we do this, we're going to define this as free fall. And free fall is anytime an object falls in a vacuum without air friction, zero air friction. But you can't ever throw a ball or drop a ball without air friction because you live on Earth and you need that air to breathe. So what the heck am I talking about? I'm talking about us cheating. Most of the time we deal with objects that are moving fairly slowly, that are relatively small. And so honestly, air friction is not that big of an effect. And so even though it's not technically free fall, we're going to treat it as if it was. We will only deal with air friction when a question specifically tells us that it is important. And usually that is only in an open-ended question where they're going to ask you to explain things. In Physics 1, we do not do any math on real movement through real air. We only deal with free fall when an object is moving without air friction. When an object is in free fall, it accelerates because of gravity and gravity only. And we can do some experiments. In fact, I'm going to make you do some experiments later this week in which we will find out that the acceleration due to gravity is about 9.8 meters per second. Or if we take a normal reference frame and choose down as negative, we would say that gravity is negative 9.8. Now, is gravity always negative 9.8? It is not. We will spend about 2 weeks talking about why gravity is not 9.8, but not now. For now, you are always going to treat gravity as negative 9.8 or negative 10. College Board generally does not care whether you use 9.8 or whether you round to 10. So go right ahead and make life easier on yourself and use 10 as the acceleration of gravity. WebAssign, on the other hand, is probably going to insist that you use 9.8. So on a test, you can use any value for gravity you want that's close to 10. But on WebAssign, I would try and use negative 9.8. Okay. In free fall, all objects accelerate at the same rate. Whether an object weighs 1,000,000 pounds or 1 pound, it will have an acceleration of negative 9.8 meters per second. Now, if you don't believe me, you can do a test on your own. Take a single penny and then take a stack of 10 pennies and just tape them together. And I want you to hold them up by your head and drop them at the same time. If heavier objects fell faster, then you would expect a stack of 10 pennies to hit the ground a lot earlier than a single penny because they're 10 times heavier. But you do it, and I'll defy you to say that there's actually a difference between the two. Or you could do a famous thought experiment. Let's say I take a tiny mass, little m, and a big mass, capital M, and I tie them together. So total, they would have a mass of m plus m. But then you have this issue of together they are very heavy, so they should fall very fast. But individually, you have a little mass holding on to a bigger mass, and shouldn't the little mass slow down the big mass? Or should the big mass be speeding up the little mass? So why wouldn't they come to kind of an average speed, an average acceleration? But then that means that their average acceleration would actually be less than the accelerating as one huge mass. And that thought experiment led people to believe that, mass can't have any effect on the falling of an object. So, trust me, gravity is negative 9.8, and it's going to stay that way until we actually deal with gravity as its own thing. So we've got some math equations, and they're all written in terms of x. And we want to like change some things up here. And we want to change them into y direction equations. So in order to do that, I'm going to take and make this Vy, and that's going to be equal to my initial y speed plus my gravity times time. Because in this case, my acceleration is the acceleration of gravity. Okay, and some of you are wondering, like, wait a minute, Sterman, you said that gravity was negative 9.8. But remember, this is all due to whatever reference frame you're working in. So this is a generic equation here. You could say that Vy is equal to Vy0 minus 9.8t. And then you would be assigning a reference frame that down is negative. You can do that if you wish. In the second equation here, we've got y equals our beginning y position plus Vy0 times t plus 1/2 gt squared. Again, gravity is now our acceleration, and I'm using it as positive for now so that you can put in any reference frame that you want. Down here, we have this equation where our ending speed squared equals our beginning speed squared plus 2 times gravity times change in y. And we have this weird equation that I told you should probably memorize. And you can say that the change in your height or the change in your y direction is equal to 1/2 v final in the y direction plus v initial in the y direction times t. Where's gravity? This equation does not have an acceleration, so gravity is not in there. Or we could say that our gravitational acceleration is equal to our change in speed over change in time. Ooh, I wrote that wrong. Our change in speed over change in time. So then the question is, well, aren't they really the same? And the only difference is that you have to remember your speed, or in this case, your velocity, should be in the y direction, where over here, you're probably talking about an x direction acceleration. It's written generically like this so that you could put it in the x direction or the y direction without changing too much. So over here, we're just going to say anytime you're talking about gravity, it's only a change in your y direction speed. All right. And some of you may ask, well, does gravity affect your x direction speed? And the answer is no. And we're going to leave that. And that's all I'm going to say about that topic until next week when we start to talk about motion in 2 dimensions. Free fall by using some real data. So to begin with, I've got Logger Pro set up here. I just opened it up and now I'm going to insert a video. So I'm going to insert a movie and I'm going to find the file that has my video in it, which is right here. And it's going to open up my video from last year. And let's take a quick look at this. It's pretty simple. It's just a ball falling to the ground. It's like a 2-second video, something like that. And that's all we need. So a couple of things we have to deal with here. One is I want to go up to options for my movie. Now, usually videos are filmed at about 30 frames per second. But I happen to know that last year we used a weird camera that has a frame per second rate of about 22.5. If you happen to know the frame per second rate of your device, then you should go to the options, the movie options, and change your frame rate. If you don't know the frame rate, leave it at 30. And that can be something that you talk about when you analyze your data. Okay. Oh, yep. Now, I want to move through this video until this ball just starts to be released. Right now it's in my hand and it's not falling at all. So I'm going to fast forward through the video here, or step through the video, I should say, watching my thumb until this frame right here. You can see that my thumb, I'll back up, just moved. So at this point, the ball is free to fall. So I've got the video in exactly the right spot that I want, and we need to start taking data by coming down here to the lower right and clicking that button. First thing I need is a reference frame, so I'm going to click on the reference frame button here. And you could put your reference frame anywhere. I usually put it right underneath the object. Another intelligent place to put it would be down here, somewhere like near the bottom of the screen. That would work, but honestly, you could put it anywhere you want. So now we have a reference frame. Now we need to teach the computer what the length scales are. So I'm going to set the scale with this button right here. And I'm going to come over and say, well, I've got an object in here which will tell me exactly what 1 meter looks like. So once I let go of the drag, Logger Pro will ask me, like, how long is that? And I'm going to say it's 1 meter. In the video that I'm going to ask you to make, you are going to be the meter stick. So you will be in the video, and I want you to go from your top of your head to your toes, and then tell Logger Pro how tall you are in meters. Okay, so I've got a reference frame. I know what 1 meter looks like, and so I'm going to start taking data by using this button right here, which is my like take data or like dot button. So I'll click that. Whenever I click over here, it's going to advance the frame 1 spot. So I put a dot in and then the ball fell. And I'm going to put a dot in and the ball's going to fall. Now you'll notice that as the ball picks up speed here, it gets blurrier. So I've decided that I'm going to always mark it at the bottom of the blur. You can do whatever you want as long as you have a consistent method for doing this, because you have to account for the error that's going to occur in your real data. So I click and the ball falls 1 frame, and I click to where I think it is now, and I keep doing that. And here I'm probably at the bottom, and now the ball is too far and it's gone. So I'm done taking data. Now, if I look at the motion map that was made here, I can tell that my ball is accelerating because the distance between my dots appears to keep getting bigger. So my motion map shows that I'm accelerating. I'm going to lie now and say that this is free fall and that gravity is doing all of the acceleration. We know that in real life there's air and there's air friction, but my ball is relatively small, it's smooth, it's a circle, so it's pretty aerodynamic, and it's really not moving that fast. So because all those things are true, air friction doesn't play that large a role, and so I can safely ignore it and not get too much error. If we were talking about a larger object or a faster object, then I would have a problem. Okay, I'm going to shrink this down and so I can get some stuff going on here. So we can see my old video here and the data appears on the graph. So we've got weird stuff going on. I've got these red points that never seem to leave 0. And that's because I set up my reference frame with the y-axis going up and down and the x-axis moving left and right, and the ball never moves left and right. So my ball never moves in the x-axis. It always stays on 0. So because of that, I really don't want it in there any longer. So I'm going to click over here on top of that Y or the X, and Logger Pro is going to ask me, what is it that you really want to see, which is just the Y. So you can see that I get a curved line here, which I expect because I'm getting faster and faster and faster. So because it's a curved line, I don't want to use the linear fit. I'm going to come over 1 and get a curve fit. And you could try all sorts of curves. You could try a quadratic, you could try a quartic, a cubic, a power graph, but I know some physics that you don't know, and I know that this is a quadratic graph. So I'm going to go right there, and I'm going to try the fit, and yes, like clearly this curve fits my points. Okay, so I've got this graph that fits the points there, but I don't just want a position graph. I want a speed or a velocity graph too. So I'm going to go up top and I'm going to insert another graph. And Logger Pro is pretty smart. It knows that if I wanted a position graph, my next graph is likely to be a velocity graph. So it pops one up there. If I really didn't want a velocity graph, I could come over here and click once on that and then say, no, I wanted something else on that axis. But it was right, I wanted a velocity graph. And as you can clearly see, this is a perfectly straight line, which I expect from my velocity graph because I have a constant acceleration of gravity. So let's come up here to linear fit, and we'll put in a linear fit, drag this out of the way, and then you all should say, wait a minute, Sterman. This at the bottom here does not look very linear. That's getting curvy. In fact, it looks like it makes an S curve as it goes down. So one thing that I do know about Logger Pro and about my method for taking data is that as the ball gets faster, I take worse and worse data. Because of that blurriness, I can't always say for sure exactly where the ball is. So what I'm going to do is I'm going to take this last piece of data here. And did you notice that my cursor became a different shape? That allows me to grab and highlight the data and say, you know what? I really want to ignore those last 2 points. Okay. So basically, only the data in the highlighted area is being calculated. All right, and you can see by the brackets here which data is in and which data is out. I could grab it and drag it over one more. That actually makes my data nicer, so I'm going to do that. I don't know how scientific that is, but as a physics teacher, it's going to help me out. So right now, I have a slope for a speed graph. The slope of a speed graph is acceleration. And in this case, my acceleration is negative 9.2 meters per second. That's pretty good because we know that gravity has a value of negative 9.8 meters per second. And so I've got about 10 or 11% error, which is not bad for real data. I also have a Y-intercept of 6.3 meters per second. So what the heck does that mean? So if I came up here and clicked on this and made this like 10, you can see that, and make this one 0, sorry, if I started at 0 seconds, that Logger Pro wants to take me all the way back to some mythical place before the video began and say that I started off in some mythical land with a speed of 6. So you have to be careful with these video things, what the data means. In this case, I have no idea what my beginning speed was because I don't really know what Logger Pro considers to be time 0. Okay, let's come over here. Here I have a curve, and this curve gives me an equation that I'm going to write down. And this equation, according to Logger Pro here, is that y, oops, that's too big. Y is equal to a t squared. That's going to be a little weird, and I'm going to put this into a form that you recognize. B times t. So I'm going to do 6.78, or actually we'll just shorten it, 6.8 times t plus this a value, which is negative 4.8. Oops. T squared. And then I have this weird C value, which is negative 2.355. So we'll call that 2.4. Now, does that look like an equation that you know? And I'm going to tell you that yes, it kind of does. We have an equation y equals VIT, V1 times t. Oops, that's a weird looking t, but we're going to keep it, plus 1/2 AT squared. And then if you look, it's also plus your y-intercept, or your beginning y position in the official equation of the whole thing. So what Lagerpro is trying to tell us is that we started off with a position of negative 2.4 meters, which is weird because if you look up here, it looks like I'm starting pretty close to 0. So I'm not quite sure what's going on there. But what's going on is that we have the same issue again. I started off at 0, excuse me, at 0.8 seconds. But what Lagerpro considers to be 0 seconds, it's now trying to figure out where I might have been. It also thinks that if we rewind the video to some place where time was equal to 0, that the ball was actually moving, but we weren't. Okay, the only thing we can pull out of here for real is this piece right here. And the reason is because this piece relies on an acceleration, which is always the same. So no matter what point in time, the acceleration was gravity. And so it doesn't matter what Lagerpro thinks is 0 and what Lagerpro thinks is 0.8 seconds. It's always going to work. So here's the thing. Our t squared term is the same, right? So what that tells us is that 1/2 of the acceleration, which in this case is g, is equal to negative 4.8. Oops. Okay, that means that g is equal to about 9.6. So g, if we multiply both sides by 2, is equal to, negative 9.6. And that's not bad. Considering our value of 9.8, the position graph gave us a value that's almost dead on, and the velocity graph gave us a value that was close, but not too bad, like 9.2. So all in all, our data is pretty good. Okay, we're going to try and use this technique a lot in the coming months, and we're always going to be looking at slopes and areas. So we will continue this as we go.